Hi, everybody. So today we are going to start chapter 4 with an introduction to projectiles. This is really going to start off with just general vector stuff, how we're going to use those with kinematics. And then the last one will actually have to do with a projectile. So this first one is about the displacement vector. Okay, so we went over this a little bit in chapter 3, but we wanted to hit on this again just to make sure that we had this perfectly understood. So you can see on the screen the displacement of the particle is the vector delta r, right? Displacement is delta r, delta x, delta s, however you want to use that variable. But the displacement is shown there. Is this the result of vector addition or vector subtraction? So remember last time we wanted to find the distance between two objects. I believe it was two airplanes. So we used subtraction that time. I want to prove here that that is what we want to do. So let's do that real quick. What I'm going to do is I'm going to trace these vectors and put them on a grid for us. So let's do this. Okay, so the red will be RF. The green will be RI. Okay. So I'm going to take this vector. Oh, I can't move it to the other slide. That's an issue. Okay, not a problem. So if we have these two vectors and we add them together, right, we are going to get a very long vector looking something like that, right? Clearly, that's not the tiny vector that we have over to the side. Now, if we subtract these, say we start with this one, and whoops, need all of that vector. And we are going to put those head to head, since I did not draw that upside down. Here, let's do this off over here. Now what happens if we draw that vector from here to here? Let's do that in gold. Okay, so this is subtraction. Remember, you should draw your subtraction with the tail on the other end, but I did not do that. Now, if we move that guy over here, what do you know? It matches, right? So vector subtraction is how you can find displacement in this case, because displacement, remember, if we want to find, let's get rid of those vectors real quick. If we want to find the displacement of an object, delta r, that would be RF minus RI, right? Or in this class, I've mostly been using R naught. I use naughts instead of I's. So we have RF minus R naught. That is how you can get a vector that looks like this. If you do addition, you're going to get a very large vector. And if you do the subtraction the other way, your vector will be going the wrong direction. So this is how you can get a displacement vector. It's doing vector subtraction. All right, next we have kinematics with vectors. Okay. So first we have a fish swimming has initial velocity of 4I plus 1J meters per second at a point in the ocean from which the displacement relative to a special rock is R equals 10I minus 4J meters. After the fishy swims with a constant acceleration for 20 seconds, its velocity is now 20I minus 5J meters per second. So we have this information. We are going to solve A, B, and C. A, show how to combine the velocity vectors to find the equation for acceleration. So we want acceleration. We want acceleration. We have V naught and V final and time, and we have some arbitrary displacement from a rock, right? Now, if we want to use those variables to solve an equation for acceleration, you could say that general is, for acceleration, is delta v over delta t, which could be shown as vf minus v naught over the time it takes, right? So we have those three. What we can do, we are using the vectors, right? Okay, so let's use these vectors. V naught is 4i, let me unit vector that, 4i plus 1j. Vf is 20i minus 5j. Now, if we want to do this section right here, Vf minus V naught, what we'll do is we will just do a stack and rack of those vectors, but we'll subtract instead of add. So we have 20i minus 5j minus 4i minus 1j. That will give you 16i minus 6j. And that is our delta V, right? That is V final minus V naught. Now, if we divide that by the time, you simply divide the entire thing by the time we had, which was 20 seconds, if I remember right. Yeah, constant acceleration for 20 seconds. So we divide this all by 20. So then we have 16 divided by 20 is 0.8i, and minus 6 divided by 20 is 0.3j. And that is our delta v divided by t, which means that this is our acceleration right there. And that would be meters per second, right? So that's how you can combine those velocity vectors to find the equation for acceleration. All we did is we used a standard kinematic equation up here, not an issue, and then we just did the math with the vectors, right? All right, part B asks, what is the direction of the acceleration with respect to the unit vector I, which really just means with respect to the x-axis, right? I is a standard distance just along the x-axis. So let's find that. What we can do is, this is going to take some trig, right? So what we could do is we could find the magnitude of the vector and then do cosine, right? So if we take the magnitude of the entire vector and then we have the entire length, then we can use cosine, then we'd have opposite over adjacent, or opposite over, no, cosine is adjacent over hypotenuse. So let's do that real quick. I'll rewrite our acceleration up here so we have that. Okay. So to draw that, we would have 0.8 along the x-axis. Oh, whoops, and then that's going to be negative, so I'll put that up top. 0.8 along the x-axis, then what I'm going to call arbitrarily 0.3 along the y-axis in the y direction, or in the j direction. Right? Now, what we can do is we need this angle right here. This is a right angle. That makes everything easier. If we need that angle, what we can do is we can find the magnitude of acceleration by doing the square root of I squared plus j squared, basically Pythagorean theorem that, right? So we have 0.8 squared plus 0.3 squared. That should come out to 0.8544 meters per second squared, right? So that is our magnitude along the acceleration vector. That's how long it is. Now, if we want that angle theta, we can say that cosine of theta, that would be the adjacent I over the hypotenuse, which is the magnitude, right? So get theta, you would have cosine inverse of 0.8 divided by 0.8544. And if I did this right, it should come out to, 20.556. So let's say 20.56 degrees. Okay. That is the long way to do it. What we can do is completely ignore the magnitude of the vector. Okay. A common mistake in doing these trig problems is you forget that you have tangent. Tangent theta is opposite, which in this case would be j, over adjacent, which would be I. We already have those. So if we did theta equals tangent inverse of 0.3 divided by 0.8, we should get the exact same thing, and we did 20.556. So we would round that to 20.56 degrees. If I were you, I would use tangent, but it's commonly forgotten about. Most people just remember that we use sine and cosine. But don't forget about lonely old tangent. Tangent is much faster. You didn't need to do that step at all if you wanted to do tangent. All right, next, what would you need to be given to use calculus instead of kinematics to find the acceleration of the fish? So what are some things that we need to do kinematics, right? Well, kinematics is going to require constant acceleration, right? You know that. That's the fundamental rule. Our general kinematic equations require constant acceleration. That we have, right? I have it circled right there, constant acceleration for 20 seconds. So that requirement is met. We have that. Another thing is that we need equations with time. That we do not have. All of these equations through here do not show any change with respect to time, because at the instant they are measured, they are not changing. Initial velocity is not changing at that time, so there's no t. It accelerates for 20 seconds, but then it stops accelerating, or we just have the instantaneous velocity. Either way, it's not shown that it's changing at the 20-second point. And then the displacement vector that we didn't even use also is just shown that you are this far from this rock at this time. It doesn't show that you're changing. So with no time in any of those equations, you can't use calculus, because calculus, if you want to find if you want to go from x to velocity, you would take the derivative of x with respect to time to get velocity. If there's no time and you take the derivative of it, you're just taking derivative of constants to go to 0. Same if you want to go from velocity to acceleration, take the derivative of velocity with respect to time to get acceleration. But if there's no time, you can't do the derivative, which is an issue, because you guys can't do integrals yet. We haven't gone over that. You might be able to, I guess. I shouldn't say you can't. Some of you are probably more than capable of doing it. I just haven't gone over it yet. Okay, so that is what you would need to do calculus on these problems. Constant acceleration and you need equations that have time in them. All right, so now we're going to go on to vector calculus. So now we will hopefully fit all of this criteria. A particle's position varies with the function r of t equals 3i plus 6t cubed j meters. Determine the function for the particle's velocity and acceleration. So to go from position to velocity, we will take the derivative of position with respect to time to get velocity. So let's do that right now. dr over dt of 3i plus 6t cubed j meters. Okay, we're just going to power rule it. 3i is a constant, so that goes away. Plus 6t cubed j, so that 3 comes down, multiply it, 6 times 3 is 18. That goes to t squared j. And then this, since you took the derivative with respect to time, you get an extra per second there, which is your velocity, right? And if you want to write that without the I component, you don't have to include that with everything. So you could say 18 t squared j meters per second equals v. That is acceptable. Then to take the derivative of that, dv of dt of 18 t squared j, you would bring down the 2. 18 times 2 is 36. Reduce your exponent by 1. Then you have meters per second squared. So your acceleration is 36t j meters per second squared. Okay. All right. So that's how we can do calculus with vectors. Now, number 2 asks, could general kinematics, like the orange equations, be used to describe the particle's motion in the j direction? Why or why not? So remember, there are 2 things we need for general kinematics. We need equations with time. We have that, right? That is a given. We just did the derivatives of those, right? Now, the other thing we need is constant. Whoa, whoops. Uh-oh. What did I do? Constant acceleration. Do we have that? Well, let's look down here. Here at our acceleration, looks like acceleration is varying with time. So that means that at time 0, acceleration is 0. At time 1, acceleration is 36. At time 2, you've already got an acceleration of 72. So that's clearly not constant. So we do not have that, and we cannot do general kinematics with this because this only met one of the criteria. So as you can see for 4.2, with kinematics with vectors, we were not able to use orange equations, but we were able to draw them and do some trig, right? We didn't have equations with time, couldn't use the orange equations. Here, we were able to do calculus with them because we did have equations with time, but no constant acceleration. So no orange equations. All right, now 4.4. I promise we will get to the orange equations and using those with vectors. We will be using kinematics, but that'll have to wait for the next video. We're just going to introduce projectiles here. So let's go to the next one, projectile intro. We have this picture here, right? Now, delta y with no gravity is shown by the equation VIT, which is right here, right? The longer vector shows that right there. Now, delta y with gravity is v naught t plus 1/2 at squared. This is one of the orange equations, right? You have delta y equals v naught t plus, 1/2 at squared. Now, if you want to show that with no gravity, like in the other equation, you would say, well, if there's no gravity, then acceleration is 0. So you take that component out, and then you're stuck with that, right? So we have two vectors. One shows the motion of an object without gravity. One shows the motion of an object with gravity. And then we have this downward vector, right, in the y direction. That is our gravity component, right? Right here. If we have 1/2 at squared, they use the vector g to show that it is a gravitational acceleration. We have this additional vector. So what they actually show is they have two vectors here. One vector shows this component, v0 t. That is the motion of an object without gravity. But if you then add, using vector addition like they did over here, then you can get the full picture, right? So if you take this vector right here, okay, take that vector, then you go head to tail with this vector, then you get the total motion of the object. They basically did the vector addition for us. So with every projectile motion, you launch an object with v0 t, right? It has an initial velocity, and it's going to travel for a certain amount of time, but then there will be this drop, right? That's kind of the point of projectile motion, is it's going to drop as it flies. So you will have this little addition there that's going to add gravity into the equation. That's why we have this vector in the y direction pulling downward. That's gravity. Now, how much acceleration occurs in the x direction? Well, for there to be acceleration in the x direction, there needs to be unbalanced forces, right? Newton's laws say that an object will continue in motion unless acted upon by an outside force. And if there's no outside force in the x direction, there is no acceleration in the x direction. And for most of our, actually for all of our projectile problems, we will have no acceleration in the x direction because that's going to require air drag of some kind to start slowing down an object while in the air. So we will most likely not do any problems like that. And if we do, it's definitely going to be one of those challenge problems that we do. Okay. All right, so this is just an introduction to what projectile motion is going to look like. In our next video, we will actually go over projectiles. We're going to call them type 1 projectiles, and then we'll go over type 2 projectiles, and I'll explain what the differences are there. But we will get into some more problems with projectiles in the next video.